Hello everyone and welcome back to my channel. This is the A+ Tutor. Today we're going over the difference quotient and how we can use the difference quotient and the limit to find derivatives. Let's consider the graph of a function that looks like this. We have some point on this graph at x equals a, and at that point there's a tangent line for our graph which would look something like this. And this line intersects our graph at exactly one point, this point at f of a. So we want to find the slope of this line because by finding the slope of this tangent line, we can find the rate of change of this function at x equals a. So that's going to tell us how fast or how slow this function is moving. If this function represents something like the speed of a train during a certain amount of time, the path that a bee takes, in their movement pattern or something along those lines, then we can use this to find the rate of change at a specific point. So if we remember when we were solving linear functions, we used a formula to find slope. Our slope formula was when we were given 2 points, m equals y2 minus y1 over x2 minus x1. We can represent this in another way if we say x1 equals a and x2 equals b, then we can say our slope is actually going to be f of b minus f of a over b minus a, because b and a, of course, when we plug that in, we will get y2 and y1. So this is going to give us the rate of change at a specific point. Well, we don't necessarily know another point on this line, but we do see that this line intersects the graph at another point over here. And we know the distance between these 2 points, let's call it h. So we can say, okay, even though we don't know for sure, what the slope of this line is, what we do know is that we have a point at a and we have a point at a plus h. So another way that we can write our slope is we can say that our slope is going to be equal to f of a plus h minus f of a all over a plus h minus a. Well, in our denominator, our a's will cancel, so we're actually going to get f of a plus h minus f of a all over h. We can rewrite this, and this actually represents our difference quotient, which you'll typically see written as f of x plus h minus f of x over h. So now let's talk about some ways that this can be applied to our function. Let's say we are asked to find the tangent line to a function at a specific point. For example, we need to find the tangent line to the function f of x equals 15 minus 2x squared at the point x equals 1. Okay, so let's consider this graph of f of x equals 15 minus 2x squared. So this is what the graph of that function looks like. And when x equals 1, our y is equal to 13. So we have this point here, which means our tangent line will look something like this. Now, this tangent line only intersects this graph at one point. So we don't have another point in order to find our slope. This means we need to use another point on our graph in order to approximate the slope of our tangent line. So let's consider that this graph, when x equals 2, intersects this point, and we have a line here between our 2 points. Now that we have 2 points, one at x equals 1 and one at x equals 2, we can approximate the slope of our tangent line. So this means this is our a, and our a is equal to 1. This is our a plus h, and a plus h is equal to 2, right? Where h is also equal to 1. So if we consider our difference quotient, which is f of a plus h minus f of a over a plus h minus a, right? Because we're using our slope formula, this would give us f of 2 minus f of 1 over 2 minus 1, which is equal to f at 2 is 6, f at 1 is 13 over 1, which is negative 7 over 1, or just negative 7. Which means our slope of our tangent line is approximately negative 7. But that's just an estimation, and we do see there's a big difference between these two lines, right? So we're able to approximate our slope, but we need to find an accurate value for this slope, and we're not going to be able to do this by using approximations of lines. But what happens if we get closer and closer to our x value? What happens if we use maybe, this point on our graph right here, or this point on our graph? We don't have exact values for that point, but what if we did? What if we could figure out as we get closer to our x value that we need to find the slope of the tangent line for? Could we use, points as we get closer and closer and closer? Well, this sounds very close to taking a limit, right? When we take the limit of something, we are looking at what the value is as we get closer and closer and closer and closer to that number. So we can do the same thing here. Let's take the limit as this distance here, as this h becomes smaller and smaller and smaller, or as our h goes to 0. So let's see what would happen if we did that. So as we said, h is the distance between x and another point on our graph. So as that h gets closer and closer to 0, the slope of our tangent line gets more and more accurate. We talked about this when we did our limits, and we want to use a limit here to find this. If we use the limit, then we can figure out the exact value for the slope of our tangent line. So all we need to do is take the limit as h approaches 0 of our difference quotient. This way we can find our exact value for our slope of the function at any point, not just at that point. So let's consider this case that we have. So if we do this for our function, that means that the limit as h approaches 0 of f of x plus h, everywhere we have an x, we're going to enter x plus h, so this would give us 15 minus 2 times x plus h squared, minus f of x, which we know is 15 minus 2x squared, all over h. So we need to simplify this before we can solve our limit. So this is equal to the limit as h goes to 0 of 15 minus 2 times, we have a perfect square trinomial, x plus h squared will give us a perfect square trinomial. So this would be x squared plus 2xh plus h squared, minus, we're going to distribute that minus sign to our 15 and to our negative 2x squared. So this would be minus 15 plus 2x squared all over h. Now we can distribute our negative 2, so we're going to get the limit as h goes to 0 of 15 minus 2x squared minus 4xh minus 2h squared minus 15 plus 2x squared all over h. Now we do have some like terms in our numerator, so 15 and negative 15 are like terms and they will cancel out. Negative 2x squared and positive 2x squared are like terms, and they'll cancel each other out. So we're left with the limit as h goes to 0 of negative 4xh minus 2h squared all over h. So now we want to simplify this further. We can factor out an h in our numerator. So if we do that, we'll get the limit as h goes to 0 of h times negative 4x minus 2h all over h. And now this allows us to cancel out our h's in our numerator and our denominator. So we're left with the limit as h goes to 0 of negative 4x minus 2h. So we are able to now plug this in and solve this algebraically. So this means when we plug this in, we'll get negative 4x minus 2 times 0, or our limit is equal to negative 4x. So this is actually going to be the rate of change of our function at any point. For us, we want to know specifically when x equals 1, what the rate of change is. So now if we plug in 1 for x, we will get -4 times 1, or -4 is our slope at that tangent line, which, if we remember earlier, we got -6 for the approximation. So this is a big difference between our -6 and our -4, which is the actual slope. So by using the difference quotient and taking the limit of that difference quotient, we're going to give us a specific value for our slope. We're going to get the actual value for our slope and not an approximation. So we did find a function for the value of the limit of our difference quotient as h goes to 0. We call that function, or the rate of change of a function at any point, the derivative. We saw it at x equals 1. We could solve it at any other point in our function and be able to then plug in a value for x to find the exact slope of our tangent line at that point. That lets us know how fast or slow the graph is moving at that point. There are lots of applications for derivatives, which we'll get into in later videos, but for today, this is the definition of the derivative. And there are a few different ways that we can express the derivative. In general, you'll typically see the derivative expressed as f prime of x, where this is finding the derivative. So if we take our example from earlier, we know that the derivative was equal to -4x, so we could express that like this. We may also see dy dx, where d dx means you're taking the derivative, so dy dx means the derivative of y with respect to x is equal to -4x. You may see y prime, g prime if we have a g of x. You may see df dx. So there's a lot of different ways that you may see it, but these two ways right here are going to be the most common. Let's take an example of finding the derivative of a function using our derivative definition. Let's take an example. Let's find the derivative of the function f of x equals x squared plus 5x minus 4. Remember, the definition of our derivative is the limit as h goes to 0 of f of x plus h minus f of x over h. So, considering our function, f of x equals x squared plus 5x minus 4, f of x plus h is going to be equal to x plus h squared plus 5 times x plus h minus 4. Sometimes I find it easier to solve our f of x plus h before plugging it into our definition of our limit, just because that fraction can get very long and very difficult to manage. So if we can solve and simplify this beforehand, it makes the work when solving for our limit a little bit easier. So solving this, we have a perfect square trinomial here in the beginning, so this is going to become x squared plus 2xh plus h squared. We'll distribute our 5, so we get plus 5x plus 5h minus 4. And that's exactly what we're going to plug into our function. To find our derivative, f prime x is equal to the limit as h goes to 0 of f of x plus h, which is x squared plus 2xh plus h squared plus 5x plus 5 minus 4, minus f of x, which is x squared plus 5x minus 4, all over h. Well, let's rewrite this and distribute that negative to our x squared, to our 5x, and to our -4. So this is going to give us the limit as h goes to 0 of x squared plus 2xh plus h squared plus 5x plus 5h minus 4 minus x squared minus 5x plus 4 all over h. So we can cancel some of these numbers out. Our x squared and our -x squared will cancel out. Our 5x and -5x will cancel, and our -4 and +4 will cancel. This means we're left with the limit as h goes to 0 of 2xh plus h squared plus 5h all over h. Now, let's factor out an h so that we can simplify this as much as we can before we solve our limit. When we factor out an h in our numerator, we get the limit as h goes to 0 of h times 2x plus h plus 5 all over h. So now our h's can cancel, and our limit becomes 2x plus h plus 5. Let's solve our limit. So by plugging in 0 for h, we will get 2x plus 0 plus 5, or we'll find that our derivative, f prime x, is equal to 2x plus 5. Using the limit of our difference quotient, we're able to find the derivative of any function. Let's take some examples, starting with this function. Here we need to find the derivative of our function, y equals 4x squared plus 1. Then we need to find the value of that derivative at 1, or f prime at 1. So remember, our derivative definition is y prime, or dy dx, or f prime of x, is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. So we'll do just that. Let's start by finding f of x plus h. Plugging in x plus h for our x, we'll get 4 times x plus h squared plus 1. We have a perfect square trinomial, so this is 4 times x squared plus 2xh plus h squared plus 1. So f of x plus h is going to be equal to 4x squared plus 8xh plus 4h squared plus 1. So now we can plug that into our definition of our limit. So y prime is going to be equal to the limit as h goes to 0 of f of x plus h, which is 4x squared plus 8xh plus 4h squared plus 1, minus f of x, which is 4x squared plus 1, all over h. So in our numerator, we'll distribute that negative 1 to 4x squared and to our 1. So we'll get the limit as h goes to 0 of 4x squared plus 8xh plus 4h squared plus 1 minus 4x squared minus 1 all over h. We have some common factors here. So 4x squared and negative 4x squared will cancel. Positive 1 and negative 1 will cancel. So we're left with the limit as h goes to 0 of 8xh plus 4h squared all over h. We can factor out an h in our numerator. So this will become the limit as h goes to 0 of h times 8x plus 4h all over h. Now our h's in our numerator and denominator will cancel. So this is going to give us the limit as h goes to 0 of 8x plus 4h. Now we can solve this limit. So since we've simplified this as far as we can plug in 0 and solve for the value of our derivative. When we plug in 0, we get 8x plus 4 times 0, which is equal to 8x, which means our derivative, y prime, is equal to 8x. Now the second step to this was to find the value of our derivative at x equals 1, or find f prime at 1. So if we plug in 1 for our x, we would get 8 times 1, which is equal to 8, which means the slope of our tangent line at x equals 1 of our function y equals 4x squared plus 1 is going to be 8. For our next example, we need to find the derivative of the function y equals negative 4x squared minus 5x minus 2, and then find the value of that derivative at 1. So remember, another way that we can write the derivative is, instead of just f prime, we can say dy dx. So that's why when we have our derivative definition here, we see dy dx. Let's start by finding f of x plus h. So everywhere that there is an x, we want to plug in x plus h. So f of x plus h is going to be negative 4 times x plus h squared minus 5 times x plus h minus 2. X plus h squared, that's going to be a perfect square trinomial, so we'll get negative 4 times x squared plus 2xh plus h squared. And then we're going to distribute our negative 5 to our x and to our h, so we'll get minus 5x minus 5h minus 2. And then we'll distribute this negative 4 to all of our terms, so this will give us negative 4x squared minus 8xh minus 4h squared minus 5x minus 5h minus 2. So now we have our value for f of x plus h, and we can plug that into our derivative. dy dx is equal to the limit as h goes to 0 of f of x plus h, which is negative 4x squared minus 8xh minus 4h squared minus 5x minus 5h minus 2 minus our f of x, which is negative 4x squared minus 5x minus 2, all over h. We're going to distribute that negative to all of our terms to the right of that negative, so we'll get the limit as h goes to 0 of negative 4x squared minus 8xh minus 4h squared minus 5x minus 5h minus 2 plus 4x squared plus 5x plus 2 all over h. Now we can cancel out our like terms. So negative 4x squared and 4x squared are like terms, negative 5x and 5x are like terms, and they cancel, and negative 2 and positive 2 all cancel. This leaves us with the limit as h goes to 0 of negative 8xh minus 4h squared minus 5h all over h. Now we can factor out an h in our numerator. So this becomes the limit as h goes to 0 of h times negative 8x minus 4h minus 5 all over h. And our h's can cancel. So we're left with the limit as h goes to 0 of negative 8x minus 4h minus 5. And we can solve this limit to find our derivative. Plugging in 0 for h gives us negative 8x minus 4 times 0 minus 5, or dy dx is equal to negative 8x minus 5. So now that we found the derivative of our function, let's plug in 1 to find the value of our derivative at 1. So y prime at 1 is equal to negative 8 times 1 minus 5, which equals negative 8 minus 5, or negative 13. So the slope of our tangent line at x equals 1 for our original function is negative 13. For our next example, we have f of x equals the square root of negative 3x minus 5. So as always, let's start by finding f of x plus h. So plugging in x plus h for x gives us the square root of negative 3 times x plus h minus 5, which is equal to the square root of negative 3x minus 3h minus 5. Now let's plug that into our definition for our limit. So f prime x will be equal to the limit as h goes to 0 of f of x plus h, which is the square root of negative 3x minus 3h minus 5, minus f of x, which is the square root of negative 3x minus 5 over h. Something to keep in mind here, when we're looking at this, it doesn't seem clear that we're going to be able to simplify this just by, the looks of it. But if we think about our binomials and multiplying binomials, whenever we have a minus b, if we multiply that by a plus b, we're going to get a squared minus b squared. So this is helpful in our case because by multiplying our numerator and denominator by the same thing but with a plus in the middle instead of this minus, we're going to be able to get rid of our square root in our numerator and be able to simplify this. So if our square root of negative 3x minus 3h minus 5 is our a, and our square root of negative 3x minus 5 is our b, then we can multiply our numerator and denominator by the same thing, just with a plus in the middle. So we'll have the square root of negative 3x minus 3h minus 5 plus the square root of negative 3x minus 5 over the same thing. So when we multiply it by something that the top and bottom is the same, this is the same as multiplying it by 1, so we can do this without changing the value of our function. So our limit becomes the limit as h goes to 0 of, we just said that this will become a squared minus b squared, so our a squared will be negative 3x minus 3h minus 5, and our b squared will be negative 3x minus 5, all over h times this entire binomial, which is the square root of negative 3x minus 3h minus 5, plus the square root of negative 3x minus 5. So now we can follow our normal process to start to simplify. Our negative side will go to our negative 3x and our negative 5, so we'll get the limit as h goes to 0 of negative 3x minus 3h minus 5 plus 3x plus 5 all over h times the square root of negative 3x minus 3h minus 5 plus the square root of negative 3x minus 5. So now we can start to cancel things. Negative 3x and positive 3x will cancel. Negative 5 and positive 5 cancel. So we're left with the limit as h goes to 0 of negative 3h over h times the square root of negative 3x minus 3h minus 5 plus the square root of negative 3x minus 5. We're able to cancel our h's, so the h in the top and bottom cancel. And so we're left with the limit as h goes to 0 of negative 3 over the square root of negative 3x minus 3h minus 5 plus the square root of negative 3x minus 5. So now let's solve that limit. When we plug in 0 for our limit, we get negative 3 over the square root of negative 3x minus 0 minus 5 plus the square root of negative 3x minus 5. So now these two square roots in our denominator are the same. This means we can rewrite this as negative 3 over 2 times the square root of negative 3x minus 5. And that is our derivative. We can rationalize our denominator by multiplying our numerator and denominator by that square root. So now we want to find the value of our derivative when x equals negative 3. So f prime at negative 3, that will be equal to negative 3 over 2 times the square root of negative 3 times negative 3 minus 5, which is negative 3 over 2 times the square root of 9 minus 5. So this is going to be equal to negative 3 over 4, which is the value of our derivative at that point. And for our last example, we need to find the derivative of the function y equals 1 over x plus 2, and then we need to find the value of that derivative at 1. So let's start by finding f of x plus h. So f of x plus h means we're going to plug in x plus h everywhere we have an x, so we'll have 1 over x plus h plus 2. Now let's plug that into our definition of our derivative. So y prime equals the limit as h goes to 0 of f of x plus h, which is 1 over x plus h plus 2, minus f of x, 1 over x plus 2, all over h. Well, in our numerator, we have two fractions. So the way that we want to simplify these and consolidate these fractions is by finding the LCD of both of these fractions. So our least common denominator between x plus h plus 2 and x plus 2 is going to be those two factors multiplied to each other. That's going to give us our least common denominator. So for our first function, we'll need to multiply our numerator and denominator by x plus 2. And for our second fraction, we need to multiply our numerator and denominator by x plus h plus 2. So that's going to give us the limit as h approaches 0 of x plus 2 over x plus 2 times x plus h plus 2 minus x plus h plus 2 over x plus 2 times x plus h plus 2 all over h. So now that we have common denominators, we can make this one fraction. So this is going to be equal to the limit as h approaches 0 of x plus 2 minus x plus h plus 2 all over x plus 2 times x plus h plus 2. All of that is over h. So there's a couple of things we can do here. First of all, we'll distribute our negative sign to all of our terms to the right of that negative sign. And we have a fraction over a fraction, so we can actually bring all of our denominators down into one expression. So this fraction is going to become the limit as h approaches 0 of, in our numerator, we have x plus 2 minus x minus h minus 2 all over h times x plus 2 times x plus h plus 2. Now we can start to cancel some of these terms out. Our x's are like terms and they cancel, and then our 2's are like terms and they cancel. So this becomes the limit as h approaches 0 of negative h over h times x plus 2 times x plus h plus 2. Now, our h's can cancel out. We don't have to do any factoring here. Our h's are able to cancel out right from there. So we're left with the limit as h approaches 0 of negative 1 over x plus 2 times x plus h plus 2. Now we can evaluate our limit. So solving our limit gives us negative 1 over x plus 2 times x plus 0 plus 2, or negative 1 over x plus 2 times x plus 2. Since we have the same factor repeated, we can represent that as x plus 2 squared. And this means the value for our derivative, our y prime, is going to be equal to negative 1 over x plus 2 squared. Now let's find the value of our derivative when we plug in 1 for x. So y prime at 1 will be equal to negative 1 over 1 plus 2 squared, which is negative 1 over 3 squared, or negative 1 over 9. So the slope of our tangent line at x equals 1 for our original function, y equals 1 over x plus 2, is negative 1 over 9. Thank you so much for watching. I hope you enjoyed and I hope you learned something. As we dive into derivatives further, we'll learn there are easier ways to solve the derivative, but this video covers just the basics in that definition of our derivative, which is taking the limit of our difference quotient. So stay tuned to learn some of our other ways that we can solve for derivatives. Make sure you're subscribed to my channel so that you never miss a video. See you there.